Hey everybody, welcome back. We're going to wrap up chapter 2 with talking about density and the temperature scales, which corresponds to sections 2.9 through 2.10. So density is defined as the ratio of the mass of an object to the volume of the object. So typical units for density are grams per milliliter, which is oftentimes reported for liquids, grams per cubic centimeters, which is used for solids, or grams per liter, which is used for gases. A density is a physical property of a substance, and it essentially describes how heavy or how light the volume of one object is compared to the same volume of another object. So I had to think of density, putting into practical terms. We're all familiar with it. If somebody asks you to pick up a 5-gallon bucket filled with cotton balls, and then they ask you to pick up a 5-gallon bucket filled with nails, you know that because nails, iron, have a higher density than cotton, the 5-gallon bucket of nails is going to be much heavier. The grams per volume or pounds per 5 gallons is going to be a lot higher than the pounds per a 5-gallon bucket of cotton balls. And so density is something we're all familiar with, but it may be new to be putting kind of these numbers and values to density as we're going to do in Chem 305. Density, because it has units of mass over volume, it's the ratio of the mass of an object to a specified volume of that object. Because it's this ratio, we oftentimes also use density as a conversion factor. So because density is this ratio of mass per volume, just like any other conversion factor that's a ratio of 2 units, density is a great way to convert between the mass and volume of a substance if you know its density. Or if you weigh an object in the lab and then you determine its volume, you can calculate its density. And so in experiment 1, you're going to be getting some practice with this, weighing objects and then determining their volume and then calculating their density. And then in experiment 2, you're going to determine the density of a series of salt solutions and make a graph to predict the density of an unknown salt solution. So in both of these instances, in experiment 1, you're going to be calculating density, and in experiment 2, you'll be using it to plot a graph and find an unknown. So let's do some examples with density. First one, this is kind of what you'll be doing in experiment 1. Let's say you have a 25 milliliter sample of, we'll just say a salt solution, sodium chloride, and you determine that 25 milliliters of this solution weighs 24.985 grams. What is the density of the solution? So we can set this up just like any other dimensional analysis problem. We're given 25 milliliters, and we're given that 25 milliliters weighs 24.985 grams. We want to find the density, and density is mass over volume. And so our plan, since we're given the mass in grams of the object, and then we're given its volume in milliliters, the plan to find density is to take the mass in grams and divide it by the volume of the object in milliliters. And that will give us a density in units of grams per milliliter. So to solve this one, we're going to take 24.985 grams of our sodium chloride solution divided by the volume of that solution, 25.0 milliliters. And you see no units cancel here. Grams and milliliters don't cancel each other out, so our final units are going to be grams per milliliter. Once I plug this into my calculator, I got 0.9994 grams per milliliter. And just like with any other dimensional analysis problem, we have to go back and check our sig figs. So in 24.985 grams, we have 4 sig figs. 5 sig figs, there we go, 5 sig figs. And in 25.0, we have 3 sig figs. So it's a division problem. So our final answer is limited by whichever number had the fewest sig figs. So 3 sig figs was the lowest amount. So we should have 3 sig figs in our final answer. So I'm going to look to the right. It's a 4. So my final answer will end up being 0.999 grams per milliliter. Is the density of this solution. So you'll get, like I said, practice doing these types of calculations in experiment 1. In that experiment in the lab, you're going to be in one part of the experiment weighing different objects and then submerging them in water to determine the volume change of the water, and that will tell you the volume of the object that you submerged. So you'll be, from lab measurements, determining the mass of the object as well as the volume, and then using those two values to calculate the density. Let's do another one. Okay, so if 0.500 liters, half a liter of sodium chloride solution, has a density of 1.0043 grams per milliliter, how many grams of sodium chloride are in the solution? Okay, so let's set this up. We're given 0.500 liters of solution, and we're also given the density 1.0043 grams per milliliter. And we want to find grams of sodium chloride. So our plan is going to be to use the equation for density to solve for the mass part of that equation. Density equals mass over volume. We're given the volume and we're given the density, so we can solve for the mass. What we need to make sure is that when we set up this equation, our units cancel out so that our volumes and our density cancel out with the V in our equation here, and that our density mass matches the mass unit here. So if our density is in units of grams per milliliter, mass will be grams and volumes will be milliliters. If our density is in grams per liters, like with a gas, then our mass would be grams and our volume would be liters. So in this case, to make this problem extra tricky, we gave you a volume in liters of the solution. And because our density is in volumes of grams per milliliter, we're going to have to get these volume units to match up. So before we can solve the problem, we're going to have to do a unit conversion. So our plan is to take our density is equal to mass over volume, but our units need to match. And right now our density is in grams per milliliter, and we want to solve for grams, but we're given liters. So we need to convert that to milliliters before we can plug it in to solve. So what I'm going to do next is convert our given 0.5 liters into milliliters. So 0.500 liters. We'll use the metric system prefix table. For every 1 milliliter, there's 10 to the negative 3 liters. So that equals 500 with a decimal milliliters. And it's with a decimal because this has 3 sig figs, 0.500. Both of these zeros count because they're after a non-zero number and they're after the decimal point. So our final answer needs to have 3 sig figs as well. So now we're ready to solve the problem. So our density is 1.0043 grams per milliliter equals the grams that we're trying to solve for divided by 500 milliliters, which we just found here was the volume of our solution. So now we have an equation set up where we have an unknown, grams is what we want to solve for. So we need to rearrange this equation to solve for grams. I'm just going to shift things up a little bit. here. So to rearrange this equation, and this should be review from algebra class, to get grams by itself on one side of the equation so you can solve for it, to get rid of this 500 in the denominator, you need to multiply both sides by 500. So if I multiply by 500, that cancels out on that side, and then I have to do the same thing to the other side of the equation. And so what we end up with is 500 milliliters times 1.0043 grams per milliliter equals the unknown amount of grams that we want to solve for. And if we check our units, you can see that milliliters and milliliters cancels out. And so we have grams equals grams, which lets us know that we set this up correctly. So once I plug that into my calculator, solving for grams, I get 502.15 grams. But this is science, so we have to check sig figs before we report our final answer. So we had 3 sig figs in 500 milliliters, and we had 5 sig figs in our density. So our final answer will be limited to 3 sig figs. So you get equals 502 grams of sodium chloride. So again, this was a density problem where you were given the density and you were given the volume of your substance, and you had to solve for the mass of the substance. But you had to do a unit conversion first because the volume and your density didn't match the volume of the substance. They didn't have the same units as the volume of your substance. So we have to make sure our units match up so that they cancel out. So we had to convert our substance volume from 5.5 liters to milliliters so it matched the same volume units as in our density. And then we set the equation up where we had our density equals mass over volume, and we plugged in the known volume of our solution, and we solved for the mass of the solution, which was the mass in grams. And then the final step was to check for the correct number of sig figs. We're next going to talk about temperature conversions. So temperature is an indicator of the tendency of heat to be transferred from one object to another. And heat will flow from objects of higher temperature to objects of lower temperature. We measure temperature using a thermometer, and there are 3 temperature scales that are commonly used. Fahrenheit, which is part of the English system, is what we use mostly in the US. Celsius, or sometimes called centigrade, and Kelvin, which are both part of the metric system. So this shows all 3 temperature scales and how they kind of compare. So on the Celsius scale, the boiling point of water is 100 degrees. Up here. On the Kelvin scale, the boiling point of water is 373. And on the Fahrenheit scale, the boiling point of water is 212. Body temperature is about 37 Celsius, 310 Kelvin, and 98.2 Fahrenheit. The freezing point of water on the Celsius scale is 0. It's 273 Kelvin is the freezing point of water, and 32 degrees Fahrenheit is the freezing point of water on the Fahrenheit scale. And then way down here at the bottom is what we call absolute zero. Absolute zero is 0 on the Kelvin scale, and this is the lowest possible temperature. What absolute zero is the temperature at which atomic motion stops. So atoms stop their natural vibration and movement. So it's the lowest possible temperature. And so the Kelvin scale is set up to go from 0, the lowest possible temperature, up to, whatever temperature you want to go up to. There's no upper limit. But because the Kelvin scale is set with 0 being the absolute lowest, the Kelvin scale can never be negative. And this will be important to remember when we do conversions between Celsius and Kelvin. It's a little bit easy sometimes to get the conversions mixed up. But something to remember is that on the Kelvin scale, if you're reporting something in Kelvin, your Kelvin temperature should never be negative, versus Celsius can have negative numbers. So the Celsius scale was set based on the freezing and boiling points of water, which makes it easy to remember. 0 is the freezing point, 100 is the boiling point. Kelvin was set based on 0 being what we call absolute 0. And then 1 degree Kelvin is the same as 1 degree Celsius. So negative 273 is the same as 0 on the Kelvin scale, negative 273 Celsius. The Fahrenheit scale was set up not based on the boiling points of pure water, but based on the freezing point of a saline solution, which is why this Fahrenheit scale is a little bit off and different than the metric scales of Celsius and Fahrenheit. Okay, so some more comparisons. Shows kind of the same thing, but with some more information. So again, there we go, there's my pen. 212 is the boiling point on the Fahrenheit scale, 100 on the Celsius scale, and 373.15 on the Kelvin scale, boiling points of water. If we look at the difference between the boiling point of the freezing and boiling point of water on the Fahrenheit scale versus the Celsius scale, it's 180 degrees Fahrenheit between the freezing point and the boiling point versus 100, which works out to a factor of 1.8, or 1 over 1.8, which is 5/9. So what that means is 1 degree Fahrenheit is 5/9 the size of a Celsius degree. So 1 degree change on the Fahrenheit scale is a smaller change than a 1 degree change on the Celsius scale. And again, we get that by taking 100 over 180 equals 5/9. 1 degree Celsius is the same as 1 degree Kelvin, which is why Celsius and Kelvin are both temperature scales in the metric system. The only difference between the Celsius and the Kelvin scale is where they start. Kelvin starts at absolute 0. That's the 0 on the Kelvin scale, but the 0 on the Celsius scale is the freezing point of water. But other than that, if you change the temperature of an object by 1 degree Celsius, it's the same as changing it by 1 degree Kelvin. The change is the same. And then absolute 0 is the temperature at which molecular motion virtually stops. Molecules and atoms stop moving and vibrating. So you'll be using the temperature scales and you'll be expected to be able to convert between the temperature scales. So I made this handy chart to show the different conversions. So if you want to convert between Celsius and Kelvin, they're both in the metric system. The only difference is where they start, right? Kelvin starts at 0 degrees Kelvin, absolute 0, and Celsius starts at negative 273, because 0 on the Celsius scale isn't where molecular motion stops. 0 on the Celsius scale is where water freezes. So the difference between those 2 points, between 0 on the Kelvin scale, absolute 0, and water freezing, 0 on the Celsius scale, is 273.15. So that's part of the conversion factor to go between Celsius and Kelvin. So converting between Kelvin to Celsius, if you start with the Kelvin temperature, you subtract 273.15 to calculate the degrees Celsius. And if you start with the Celsius temperature, you add 273.15 to calculate the Kelvin temperature. So this is where I said sometimes you forget, like, oh, do I add or subtract 273.15? If you're calculating Kelvin, you should never get numbers less than 0. So if you forget and you take Celsius and subtract 273.15 and you somehow end up with a negative number, it's a clue that you did the wrong conversion, because Kelvin temperatures can't be less than 0. Okay, for going between the English and the metric system, we convert between Celsius and Fahrenheit. So if you're starting with a Fahrenheit temperature, you subtract 32, and then you divide by 1.8. And remember that 1.8 comes from the ratio between the difference in the freezing to boiling point of the Celsius scale versus the Fahrenheit scale. So you take your degrees Fahrenheit minus 32 divided by 1.8 to calculate your Celsius temperature. And to calculate Fahrenheit temperature, you could take this top equation, just rearrange it to solve for degrees Fahrenheit, which is what I did down here. So if you're starting with degrees Celsius and you want to convert it to Fahrenheit, you take your Celsius temperature and you multiply it by 1.8, and then you add 32, and that will give you your Fahrenheit temperature. So converting between Celsius and Fahrenheit is a metric to English system conversion, and it involves addition or subtraction. So you really need to pay attention to sig figs on these. Because it's between the two different systems of measurement, the English and the metric system, you have to keep track of the sig figs. The way to do this, because it involves addition and subtraction in addition to the multiplication or division step, is that the 1.8 and the 32 are assumed to be exact numbers. They're exact because of that ratio I showed you, 1.8, the temperature difference, the ratio of the temperature difference on the Fahrenheit scale to the Celsius scale between freezing and boiling points. And then the plus 32 comes from because the freezing point on the Fahrenheit scale is 32 versus the freezing point on the Celsius scale is 0. So there's a difference of 32 between them. These numbers, 1.8 and 32, are exact numbers. And so they're not going to affect your sig figs. So the only thing that's going to affect your sig figs when you're converting between Celsius and Fahrenheit is the number of sig figs on your starting value. So if you start with, say, 1.8 degrees Celsius, because this problem involves addition, when you add numbers that have sig figs, you have to pay attention to the precision of the numbers that you're adding. It's not based on the total number of sig figs, it's based on the precision. So if you start out with a number like 1.8 degrees Celsius that has precision out to the 10th place, your answer in Fahrenheit will also go to the 10th place because your Celsius had precision out to the 10th place, and all the other numbers involved in the calculation are exact numbers. Same thing going from Fahrenheit to Celsius. Let's say you start with a Fahrenheit temperature of 35 degrees Fahrenheit. Your precision is in the ones place. So that means your ending temperature in Celsius will also go to the ones place. So when you're figuring out sig figs for these Celsius to Fahrenheit and Fahrenheit to Celsius conversions, pay attention to the precision of your given value. If your given value, like you're starting out with Celsius, goes out to the 10th place or the 100th place, then that's how far out your Fahrenheit temperature will also go, and vice versa if we're going from Fahrenheit to Celsius. When you're converting between Celsius and Kelvin, or Kelvin and Celsius, it's also an addition or subtraction problem. So 273.15 is not exact. So you have to pay attention to the precision of both your measurement, as well as if your measurement is more or less precise than out to the hundredths place. Because we use 273.15, it goes out to the hundredths place. None of your answers here should go past the hundredths place. Like let's say you had a really, really precise thermometer in the lab. You read that your boiling point of water was 100.0001 degrees Celsius. Even if you had this much precision on your initial measurement in the lab, because we're adding it with 273.15 and the 5 ends in the hundredths place, your final answer would be cut off in the hundredths place. If you had a number that was less precise, let's say you had a not very precise thermometer and you read that your temperature was 100 degrees Celsius, no decimal point, so your last sig fig is in the hundredths place, then when you converted that 100 degrees Celsius plus 273.15, you'd get 373. It would round to just 400 with no decimal point Kelvin. So temperature conversions, most conversions are based on multiplication. like what we've been doing so far, but temperature conversions have that addition or subtraction step, so you have to pay a little bit more attention to the sig figs. So again, to keep track of sig figs for temperature conversions, it's based on the temperature with the fewest digits past the decimal point. So pay attention to the precision of your measurements when you're doing temperature conversions, because when you're dealing with sig figs with addition or subtraction, it's based on the precision of the measurements. How far to the right does the measurement go? How far to the right of the decimal point does the measurement go? Okay, so let's do a few practice problems with temperature. So let's take 102 degrees Fahrenheit to Celsius. So our conversion for going from Fahrenheit to Celsius, degrees Celsius equals our degrees Fahrenheit minus 32 divided by 1.8. So if we have 102 degrees Fahrenheit, we'll do 102 minus 32 divided by 1.8. And I get 39 degrees Celsius. And I'm going to cut this off at the ones place because my Fahrenheit that I began with only had precision out to the ones place. Okay, next one. We have 0 Kelvin and we want to convert it to Fahrenheit. We don't have a direct conversion between Kelvin and Fahrenheit, so we're going to convert Kelvin to Celsius first and then Celsius to Fahrenheit. So to go between Kelvin and Celsius, degrees Celsius equals Kelvin minus 273.15. So we're going to take our 0 Kelvin minus 273.15 equals negative 273.15 degrees Celsius. And now we're going to take our degrees Celsius and convert that to Fahrenheit. So degrees Fahrenheit equals degrees Celsius times 1.8 plus 32. Can line that up a little bit more. Okay, so now that we have our degrees Celsius, we're going to convert that to Fahrenheit using the conversion factor we just wrote. So we have negative 273. Let's keep track of our sig figs here. A really important step in this problem. So we had 0 degrees Kelvin, which ended in the ones place. There was no decimal point. There were no digits past the decimal point. So that means this 273.15 has to end in the ones place. So we're going to keep track of that. 0.15 degrees Celsius times 1.8 plus 32. And I get negative 460 after I round to the ones place. Let me just try that again to see what I got before rounding so you can follow along. 273.15. So before I rounded, so we can show the whole thing. Before rounding, I got negative 459.67 degrees Fahrenheit. But since 273.15 ended in the ones place, my final answer needs to also end in the ones place because these temperature conversions are based on the precision of the measurements. So the final answer equals negative 460 because we have to round. Okay, last one. This is my favorite temperature conversion. You can have such a thing. Okay, so we have negative 40 degrees Celsius to Fahrenheit. So we're going to use our Celsius to Fahrenheit temperature conversion here in orange. So we have negative 40 degrees Celsius times 1.8 plus 32. And you end up getting negative 40. And we need to keep this with the same precision as the number we started out with. 40 degrees Celsius was in the ones place. So we want our final answer to also end in the ones place. So negative 40 is where the Celsius and the Fahrenheit scales exactly intersect. So if you do trivia, that's oftentimes a trivia question, you know, at what temperatures Fahrenheit and Celsius equal? It's negative 40. Okay, so some general help with sig figs and math review in your lab manual in Appendix 2 and Appendix 3. There's a kind of a 1 or 2 page sheet on reviewing significant figures as well as logarithms and exponents. And just remember, if a problem asks you to use proper sig figs, or if a problem has units in it, you have to pay attention to and follow the rules for doing calculations with significant figures. If a problem has units in it, you need to check the units to think, okay, do these units represent an exact number, like a counted object or a definition, or are these units representing a measurement? And anytime you have a measurement, you're going to have to take into account the sig figs and follow the rules for sig figs if you're multiplying, dividing, adding, or subtracting that number, so that when you get to your final answer, you can round it to the right number of sig figs. So to wrap up chapter 2, something for this chapter I think is really handy is to jot down 3 key concepts that you learned, and then also jot down 3 key concepts that you want to work on or study more. And the ones that you learned, you can kind of check off your list. Okay, I've got these ones and I'm good. And then if there's anything you want to work on or study more, take the time now, early in the class before your schedule gets really hectic, before we start getting into more complex chemistry. Take the time now to make sure you really understand sig figs and rounding and doing these calculations. Because as I've said, from this point on, when you do a calculation, it's automatically expected that you're going to report the final answer with the correct number of sig figs. Okay, that's it for chapter 2. Thanks for going through it with us. We'll start with chapter 3 next.